One thing that we should have got from our car crash video is how to calculate impulse. So I'm going to give us an awesome example with a baseball being impacted by a baseball bat. In this case, it's a really big force, 100 newtons to the left, and it acts for a very small time duration, 0.02 seconds. How to calculate impulse then is the product of force times time. The arrows over force and impulse indicate that those have direction that matters. Even though the arrow points to the right, that's just a symbol indicating that you should take into account direction in that number. The negative impulse is because the force was acting to the left. Where this equation comes from is that when I'm doing this baseball impact, the force is a constant value. It stays the same number the whole time. As a result, taking the product of force times time, that looks an awful lot like an area under the curve, where the force is the height and the time is the base. This equation for force times time as a product can only be used for constant forces. It can't be used if I get an irregular graph or a force that changes over time. So let's say that I am pushing an object and I'm just getting weaker and weaker and weaker. I start strong, I get weaker, and I still want to determine the impulse. Well, if I take the impulse, which is the average force times the time, notice that the average force is simply half of the maximum. But since time is the base of this triangle and F max is the height, well, then impulse is truly the area under this curve of the triangle from the x-axis upwards. You're going to use this equation whenever you're given a graph problem or a force that changes over time. So let's use this area under a curve method. Let's say I push an object with 10 newtons of force for 2 seconds and then gradually get weaker over the next 2 seconds. I have a rectangle and a triangle area. The rectangle has a base of 2 and a height of 10 newtons, whereas the triangle has a base of 2 and a height of 10 newtons. Mathing this out, I have 20 newton seconds of impulse from the rectangle plus 10 newton seconds of impulse from the triangle to make 30 newton seconds of impulse total. Notice that this impulse is positive because the area we're dealing with is this area above the x-axis. This means I must have had a force acting in the positive direction. Either a force up or a force right would give me a positive impulse. One thing you're going to find from today's practice, though, is unfortunately, most real collisions do not make regular graphs that we would want to take the area under a curve for. We want to take the area under the curve from the x-axis upwards, and for an irregular shape like the Gaussian shown here, what I want to do is I want to approximate this as a triangle. Notice that when I shade this, sometimes it overestimates, sometimes it underestimates, and in general, that's going to get us close enough to the actual impulse. So this is a triangle. In this case, I have a base of 9 minus 1. My base of time duration would be 8 seconds. The height would be the maximum force, and let's call that 25 newtons. That means calculating the area under the curve would be 1/2 base height, or 1/2 8 seconds times 25 newtons for an impulse of 100 newton seconds. This is giving me a positive impulse, which means I either had a force acting right or up, some sort of force in the positive direction. Since real-life collisions look like this, we're going to be observing them in two different ways, either by pivot for the kids at home or in person for the kids that are here. If you're working on this in pivot, you're going to be looking at the force versus time graphs of various collisions and reading off the force, time duration, and impulse. So let's say we do trial A, light cart into wood wall. You would fast forward in the video until we see the collision. And in the background, you see that we've actually already highlighted the integral for the force. The integral is actually telling us the impulse. Impulse, integral, they both start with I. So this trial, I would be writing down an impulse of 0.591 Newton seconds. I'd be writing down a maximum force. So notice, do you see the word max right here? I'd be writing a maximum force of 45.74 newtons. And finally, to get the time. The time is a little bit rough to see here, but essentially what we do is each division on the graph is 0.02 seconds. Therefore, in this graph, I see somewhere between zero point 0.02 and zero point 0.04 seconds. And if we want, we can highlight those sections. So this vertical line is at 0. This vertical line is at 0.02. The last vertical line is at 0.04. So I would measure this time duration as approximately 0.03 seconds. From this graph, I can get the impulse from the integral, the force from the max reading, and the time from reading off how many segments are on the x-axis. Finally, for my students that are in school today, we're going to be using a program called Graphical Analysis on your iPad to actually measure these forces and times and impulse with real collisions. So what you need to do is download Graphical Analysis from self-service, open it up, and hit Sensor Data Collection. Then you're going to connect wirelessly to the cart that your group has. Read off the serial number and make sure you're connected to your cart, not somebody else's cart. Once you've done that, you'll be able to connect to a sensor.
I click Sensor Channel, unclick Position, and read Force instead, and press Done. Now when I do this, I'm going to select Force as my y-axis, and I'm actually just going to completely ignore the bottom set of data here. I'm only looking on the top graph. When my cart has a collision, it makes a very large negative force, which is not necessarily what I want to see. I wanted to see that upward curved graph from earlier. So I'm going to hit force Y down on the bottom right and hit reverse and 0. This way, when I hit collect again, that the force I've collected is a positive and curved force. Finally, let's get what we need to get from this. I want the impulse, force, and time from this graph. When highlighted, I can see the time is approximately 0.14 seconds. So that's the time. The maximum force that this collision had, if I click on the top of this graph, the maximum point up here, the maximum force was 7.26 newtons. And finally, the impulse. I don't really want to calculate the area under the curve here, so what I'm going to do instead is highlight the section of the graph. The impulse is 2.62 newton seconds. So that's how you measure force, impulse, and time from a curved graph of data.
So let's wrap this up. There are 3 ways to calculate impulse. We can use the impulse is equal to the product of force times time. We can use this whenever we have forces that are constant. In this case, the arrows on force and impulse indicate that those are both directional quantities. If I'm given some sort of graph, I would use area under the curve to calculate impulse. A force versus time graph would have an area under the curve equal to impulse. Later this week, we'll talk about a third way to find the impulse, and that's taking the change in momentum. But today's work, we're going to focus just on the first 2 methods. Best of luck!